Imagine you're in a spaceship. You fire your engines and accelerate to half the speed of light. Then you fire them again. Same thrust, same duration. You should now be going at the speed of light, right? But you're not. You're going at 80% of the speed of light. You fire them a third time. Same thrust, same burn. Now you're at 93%. No matter how many times you fire those engines, you never reach 100%. It's like the universe is playing some kind of cruel trick on you. But it's not a trick. It's something much stranger. Most people think the speed of light is a speed limit, the way a highway has a speed limit. Some rule that says you can't go this fast. And the explanations you usually hear kind of reinforce that. You'd need infinite energy. Your mass becomes infinite. These aren't wrong, exactly, but they make it sound like the universe is just blocking you. Like, if you had a big enough engine, maybe you could break through. But that completely misses the point. The speed of light isn't a wall you can't break through. It's not a barrier at all. It's a feature of how space and time actually work. If you watched our GPS video, you saw that time itself runs differently depending on how fast you're moving. The Lorentz factor, gamma, equals 1 over the square root of 1 minus v squared over c squared. That wasn't just a GPS thing. That's spacetime telling you something fundamental. And today, we're going to understand what it's really saying. Okay, let's build this up step by step. Start with something simple. You're standing still, and I throw a ball at 10 meters per second. You see it moving at 10. Easy. Now you're walking toward me at 2 meters per second. You see the ball coming at 12. We just add the speeds. This is called Galilean relativity, and it works perfectly for everyday life. But light doesn't play by those rules. Back in 1887, two physicists, Michelson and Morley, ran a brilliant experiment. Everyone assumed light traveled through a medium called the ether, like sound through air. And since the Earth is hurtling through space, they figured light should travel a tiny bit faster in one direction than another, like swimming with the current versus against it. So they set up a beam of light, split it in two, sent the halves along perpendicular paths, and bounced them back with mirrors. If the ether was real, the two beams would return at slightly different times, and they'd see a telltale shift in the interference pattern. They found nothing. No shift, no ether wind. The speed of light was exactly the same in every direction. They tried again. Same result. Other physicists tried. Same result. It broke physics for 2 decades. Then in 1905, Einstein did something radical. Instead of trying to explain the result away, he took it at face value. He said, "Fine, the speed of light is the same for everyone, period. It doesn't matter if you're standing still, flying at half the speed of light, or orbiting a black hole. You always measure light moving at about 300,000 kilometers per second. Always." So here's the question. If speeds don't just add up normally, what happens instead? Let's say you're on a spaceship going at 90% of the speed of light. You turn on a flashlight. Does the light come out at 1.9 C? Nope. You measure it at C. An observer on Earth also measures it at C. Same speed. Both of you. How is that possible? Here's where it gets beautiful. For both of you to measure the same speed of light, something else has to give. And what gives is space and time themselves. Let's start with time dilation, and I want to show you why it happens, not just that it does. Imagine the simplest clock you can build. Take 2 mirrors, one above the other, and bounce a single photon of light between them. Each time the photon hits a mirror, tick. That's your light clock. Now, put that clock on a spaceship moving sideways. From your perspective on the ship, nothing changes. The photon just bounces straight up and down. Tick, tick, tick. But watch what happens from Earth's perspective. The ship is moving, so in the time it takes the photon to go from the bottom mirror to the top mirror has slid to the right. The photon doesn't travel straight up anymore. It has to travel along a diagonal to reach the mirror, a longer path. And on the way back down, another diagonal, an even longer total path. Here's the key. The speed of light is c for everyone. The photon can't speed up to cover the longer diagonal. It has to travel at c. Same speed, longer path, means more time between ticks. The moving clock must tick slower. This isn't a trick or an illusion. It's geometry. Pure, unavoidable geometry. And the faster the ship moves, the longer the diagonal gets, and the slower the clock ticks. At 90% of c, your clock runs at less than half its normal rate. At 99%, about 1/7. Second, length contraction. Space itself compresses in the direction you're moving. This one follows from the same logic. If time is running slower on the moving ship, but the speed of light has to stay constant, then distances must shrink to compensate. Speed is distance divided by time. If time changes and speed can't, distance has to change too. At 90% of c, distances in front of you shrink to less than half their rest length. The universe literally gets shorter ahead of you. And this isn't just theory. Nature gives us a beautiful proof: muons. High-energy cosmic rays slam into the upper atmosphere and create particles called muons. We know how fast muons decay. Their half-life is about 2 microseconds. Even traveling at nearly the speed of light, a muon should only make it about 600 meters before it decays. But the upper atmosphere is about 10 kilometers up. They should never reach the ground. And yet, muon detectors on the surface pick them up all the time. Why? Time dilation. From our perspective on Earth, the muon's internal clock is running so slowly that it lives long enough to make the full trip. And from the muon's perspective, it experiences normal time. But length contraction has squished 10 kilometers of atmosphere down to a few hundred meters. Same result, 2 different explanations, both perfectly consistent. That's how you know this is real. Now, here's the real insight. Forget thinking of space and time as separate things. They're woven together into a 4-dimensional fabric called spacetime. And in spacetime, everything is always moving. You, me, this spaceship, we're all moving through spacetime at the same total rate. Always. The speed of light, c, isn't just a speed limit. It's the rate at which everything moves through spacetime. When you're sitting still in space, all of your motion is through time. You're barreling into the future at the maximum rate. But when you start moving through space, you're diverting some of that motion away from time. The faster you move through space, the slower you move through time. It's like a budget. You've got a fixed amount of space-time velocity, and you have to split it between space and time. That's why your velocity gauge behaves so strangely at the start. Each engine burn adds energy, but instead of making you go proportionally faster through space, the energy gets split. Some goes into spatial speed, but more and more goes into warping your relationship with time. You're trading time for space. And reaching the speed of light, that would mean putting all your motion into space and none into time. Your clock would have to stop completely. For anything with mass, that would require infinite energy, not because of some arbitrary rule, but because you'd be trying to completely opt out of time. Only massless particles like photons can do that. They move entirely through space, at c, and they experience 0 time. And there's a formula that makes this crystal clear. A particle's speed equals its momentum times c squared divided by its energy. For anything with mass, the energy includes that famous mc squared term, which means the energy is always bigger than the momentum part. So the fraction, your speed, is always less than c. You can pile on as much momentum as you want. The energy just grows with it, dragged up by that mass term. The fraction creeps closer and closer to 1, but never reaches it. But for a photon, no mass means no mc squared. The energy just equals the momentum times c, so the speed equals pc squared over pc, which is just c. Exactly. Always. A photon doesn't travel at c because it's somehow fast enough. It travels at c because having zero mass means the math gives it no other option. Mass is what gives you the freedom to go slower. For a photon, the moment it's emitted and the moment it's absorbed are the same instant. So let's go back to our spaceship. You fire your engines over and over, and the speedometer barely moves. It feels like the universe is fighting you. But now you know what's actually happening. You're not hitting a wall, you're rotating your direction through space-time. Every burn tilts you a little further from time and toward space. But you can never tilt all the way, because you can't stop moving through time entirely. And this isn't just abstract physics. This is the same effect that makes GPS satellites need relativistic corrections, something we covered in our last video. It's the reason particle accelerators like the Large Hadron Collider can push protons to 99.9999% of the speed of light, but never to 100%. It's why cosmic rays, particles from exploding stars, cross the entire galaxy in what feels like seconds to them, even though millions of years pass for us. They've traded almost all their time for space. The speed of light isn't a cosmic speed limit posted on some sign. It's the total rate at which everything, you, me, light, the whole universe, moves through the fabric of reality. The speed of light isn't about what you can't do. It's about what the universe is. Space and time are linked. Your motion through them is shared. And that single fact explains time dilation, length contraction, and why nothing with mass ever reaches c. Next time on Eigenstate, we're going deeper into the quantum world, where particles don't even have a definite position until you look at them. If you don't want to miss that, subscribe and hit the bell. And if this video changed how you think about speed and time, drop a comment. I'd love to hear which part clicked for you. See you in the next one.